so if you need to pause the video, it's a little lengthy. Read it. Here's A, B, and C. All right, I'm just going to give you a quick summary of it. Here is a block of mass M. It's going to be compressed to the right, pushing the spring, and the work that is done on the block would be stored in the spring as PE spring, and then it's going to let go, which means it's going to cause the block to shoot leftward. And as it travels across this flat horizontal surface, it states that it's frictionless until it gets to reach the point B, capital B here before bottom. And then as it travels from the bottom of the loop all the way up to the top of the loop, it does have friction acting on it. And then at the top, here's VT. Other than that, let's go ahead and crack it out. Okay. Part A asks us to find the spring, the initial compression of the spring, or this variable x here in the diagram. So to do that, I'm just going to set up conservation energy. I want to take the reference here of the spring as my initial, and then point B being my final reference point before it enters the loop. Okay, and again, keep in mind that this flat surface here is frictionless, so therefore this is pretty easy to do. All you have to do is set up your conservation mechanical energy, MEI equals MEF, and then I'm just going to introduce all the energy terms here on the left side and right side. So PE gravity plus KE plus PE spring initially, and then on the right side is the same term but just has an F. So PE gravity final plus KF plus PE spring final. Okay, but here let's cross out things that does not exist. The block starts on the horizontal surface, which has no height. Therefore, PE gravity gets crossed out. It starts at rest, so I'm going to cross out KEI. The only term I want to keep is PE due to spring, because again, there must have been a force pushing this block to the right. Force displacement does work. That work is stored in the spring, so therefore there is energy stored in the spring. All right. Other than that, I want to cross out PEGF as well, because there is no height at point B for being bottom of the loop here. We do have KF though, because the diagram indicates that the block is moving, or just using common sense. Once the block gets past its equilibrium position, it's going to go ahead and continue sliding, and then goes up the loop and then comes back down. Okay. PE spring, it does not exist at point B because the spring is no longer affecting the motion on the block. Other than that, the left side is just PE spring. The right side is just KE. Hopefully after you practice for a while, you don't have to write all the terms out. You just have to know where the energy comes from. Like if I would just say the energy stored in the spring is the kinetic energy at point B. So you can just make these statements pretty quickly, hopefully as you practice, without writing all this stuff down all the time. All right, I want to break up P spring to 1/2 kx squared, and then Ke is just 1/2 mv at point B squared. The halves cancels out. The question asks for x, so I'm going to go ahead and isolate for x squared first by dividing both sides by k. So I'm just going to move k down to the bottom right in this function. This is x squared. Well, we know what m is. We know what VB is. VB is given in the problem as 13.8. K is 450 newtons per meter. And then the mass, once again, is 0.5 kilogram. And all this is in the wording, which I hope you pause and read. All right, I'm just going to plug things in. 0.5 for mass, V for 13.8. This is speed. And we're going to square that, divided by 450. If you do that, x squared itself will be 0.2116. But then to get x by itself, we need to square root both sides. So therefore, the square root of x squared is just x. And then we need to square root 0.2116. And then the answer there will be 0.46. And that is the compression of the spring. All right, part B. Part B asks you, or states, if the block reached the top of the track, what would its speed at that point be? So here is V at the top. Again, T for top. So let's go ahead and set it up. Okay, the statement is slightly different than part A, because if you read the problem like I suggested, once it gets to point B, as it travels up along this circular segment of the vertical loop, there's friction. It says here an average frictional force of 7 newtons. Okay, well, if there's friction, that means energy has to be taken away from the system. So here in my statement for part B, I have the initial mechanical energy, which is stored in the spring, minus the energy lost as it travels up the left side of the vertical loop, and the leftover is the energy at the very top of the loop. So here, I'm just going to break it up. Keep in mind there is friction against this left side of the loop, okay? So This is now my final reference point, so I'm going to start at the spring again as my initial. If you want to, you can actually start at point B as your initial because the energy is the same as we concluded, right? The energy stored in the spring here is the same as the kinetic energy at point B. But I'm just going to keep my initial the same, which I'm just going to use the spring as my initial. And then my final reference frame would be at the very top of the loop-the-loop. So here, I'm just going to break up. MEI is simply due to the spring. So I'm just going to leave everything else out that we cross out over here. I don't want to write this whole statement again. Therefore, I can just say the energy stored in the spring minus the energy that is lost as it travels up the vertical loop will equal to PE. Well, there's a PE because there's a height and it's moving, so there has to be a KE. Right? So I keep terms that exist. So therefore, I'm just going to go ahead and expand this stuff again. PE spring is 1/2 kx squared. We already found x in part A. Here, I just broke up the work due to friction. It's simply due to the force of kinetic friction times the displacement. And then PE here is just mgh, and then KE is just 1/2 mv squared. I did highlight this HF because keep in mind this is HF, right? So using common sense, the R, the radius of the loop is 1. So therefore from bottom to top of the loop, that is a distance of 2r. So r being 1, so the distance here being 2, or the diameter of the circle being 2. Okay, keep that in mind. All right, other than that, I'm just going to plug in values without units here because I'm running out of space. 1/2 gets carried down. Spring constant is 450, that's given in the statement. X is 0.46, which I calculated in part A. Don't forget to square that. Here, the average kinetic frictional force is given in the problem as 7 newtons. So here's the 7. And then I highlighted this one because this is just using your prior knowledge here. Well, what's your delta X? Well, from B all the way to the top is half of a circle. So the circumference of a circle is 2 pi r. That explains the 2 pi r on the top. Well, why is there a divide by 2? Well, because it's only going half of the circle. Okay, so 2 pi r is the circumference. I'm going to take the circumference divided by 2 because from lowest point, the highest point, that is the distance of half of a circumference. So that explains that. All right. And that on the right side, M is 0.5, G is 9.8. H here, once again, is 2 because the height is the diameter and the radius being 1, diameter is 2. All right. And then here, M is 0.5. So as you can see, the only thing that I don't have here is VF. So I'm just going to simplify everything on your calculator. I want to cross out those 2's because the 2 on the top and bottom cancels out. If you punch in 1/2 times 450 times 0.46 square, you'll get 47.61. And then if you do 7 times pi times r being 1, you'll get 22, or about 22. And then 0.5 times 9.8 times 2 is just 9.8. And then 1/2 times 0.5, which is just 1/4, which is 0.25. Here, I'm just going to combine like terms. We have 47.61 minus 22. But then you see this 9.8 on the right side. Well, this 9.8 doesn't have a VF or anything. So I need to get rid of this 9.8. So I'm going to move this 9.8, which is positive on the side. I'm going to move to the other side, which makes it negative. So really, I have 46.61 minus 22 minus 9.8. Okay, so if you do all that, you'll get 15.81, and that'll equal to 0.25 VF squared. Well, to get VF squared by itself, the next step is to divide both sides by 0.25. So if you put in 15.81 divided by 0.25, you'll get 63.24. But this is VF squared. But so therefore, to get VF by itself, we square root both sides. And the square root of 63.24 will give you about 7.95 meters per second. So that's the speed at the very, very top. Okay, so that's the answer to part B. Now, part C asks us, does the block actually reach the top of the track? Or does it fall off before reaching it? Well, how do you answer this type of question? To answer this type of question, you have to find what the minimum velocity is. Okay, so here in my statement, I say yes, it will make it over because I can prove it. Okay, well, here's how you prove it. Well, at the top of the loop, there is an f of g pointing down the page. Okay, this block here is on the inside of the track, which means the track is going to push down on it as well. That is typically your net force at the top of the vertical loop-to-loop. However, in order to figure out if it does reach or not, you have to find the minimum speed needed in order to make it over. So, typically, at the very top, you have f of c equals the f of g plus f of n. F of c is the net force pointing towards the center of the circle, right? In this case, both these vectors are pointing towards the center, so we add them. However, well, in order to figure out if it falls off or not, I need to figure out what the minimum velocity needed is. So I want to cross out f of n. I need to find v min. So to find v min, the only way to get this sum on the right side to be a minimum is to get rid of one of these terms. Well, you cannot get rid of f of g. The only thing you can get rid of is f of n, because minimum velocity would suggest that it's on the verge of losing contact with the track. Well, f of n is the force exerted if you're touching. So on the verge of, losing contact would imply that f of n is 0. All right, other than that, I'm just going to go ahead and take this vector off the diagram here, draw it, but then know when to erase it. Here, I want to get rid of f of n because it said to prove it. I need to find v min. To find v min, the only force that exists on the block at the top is f of g. So therefore, I want to substitute out f of c for mv squared over r. F of g is simply mass times gravity. Mass cancels out. So therefore, this v squared here is what I'm trying to find. So I want to multiply both sides by r. And then this is v squared. So to find v, we need to square root both sides. So therefore, v is just equal to the square root of gr. Well, here I know g, I know r, g being 9.8, r being 1 because it's given. And if you do that, you get a value of 3.13 meters per second. Now, it's important to keep this in mind. This v here, this is the minimum velocity that you need. So let's say, for example, anything greater than this will work, like 3.14 works, 4 works, 5 works, 6 works, 8 works. So this is how much you need. This is how fast you need to be moving at the top. If not, you actually will physically fall down, okay? Because this value of 3.13 is less than what I got in part B. I think on part B, I got the answer 7.95, okay? So because 3.13 is less than what I have, it'll make it over because the speed at the very top is 7.8, which exceeds what you need, right? Because what you have is more than what you need, it will make it over, okay? If you need to listen to that again, hit pause and rewind. Good luck, stay nerdy, don't be whack.